Okay, so on this video we're going to talk about what do you do when the process that you're interested in doesn't actually call for one of the major welding processes. You know, if it's not GMAL or something else, what do you use? Well, let's take a look at some other less common operations. More highly skilled folks would be doing some of these. But we've got things when you're dealing with situations where you have, you're really concerned about weld purity, the amount of heat you put in, the properties of your base metal. You may have to use less common stuff. So with that, we can talk about real quickly the Submerged Arc Welding, or SAW, Stud Arc Welding, which we have mentioned previously on our welding symbols, Electron Beam Welding, EBW, Laser Beam Welding, Ultrasonic Welding, Friction Welding, and of course Brazing Welding. So these are processes that are a little bit more, they're not uncommon, they're just not necessarily part of the mainstream lot of applications. So let's take a look real quickly at these. In submerged, occurs under a shield of granular flux that covers the arc and the filler material. This allows deep penetration, heavy disposition, and of course you're in direct current. So, electrode positive. The process automated with weld possible in the flat and horizontal positions. So, in this case we don't actually have some examples of which, but in SAW would be called out for specifically by the designer, and they're actually using it, and submerge obviously results from the fact that it's covered by flux. Now, in the SW, in the stud welding, so basically, and as we've seen before, you take a stud, let's just draw one out here, you run some current through it, you make contact with your base that you're going to do, the current running through it creates the resistance, heats this up, and it melts it to it, the pressure helps binding in there, you release and let it cool, and you've got studs sent to it. Automated process, the pressure is a big part of the process being fused together, and it can be done in one big operation. So it's more like resistance welding in the fact we're just flowing electricity through it, but in this point of contact where the electricity is moving through, that's where we get our fusion occurrence. All right? Electron beam welding. So this one's really cool, and you can always Google this and YouTube this if you want to see how it occurs. High-powered dense beam of electrons, and they are joined. The energy of the electrons is changed to thermal energy at the weld area, causing the weld to melt and fuse together. Electron beam welding is a really, really cool thing. One application of electron beam technology is the fact that we can use this kind of concept to do metal 3D printing. So we can actually use metal powder and hit it with a high energy beam and actually start to fuse powder together and form an object. So metal printers can actually use this technology very effectively. Laser beam, same concept, you're still, hit the wrong button, sorry. Same concept, you're still doing a concentrated beam of light, except it's in the weld area, heat generated by the beam of light provides a great degree of weld accuracy. Same concept, except we're using a laser versus a high density electron beam. And you may say, what's the difference? There are some actual differences, but the key thing is your electron beam probably is going to involve way more energy than the typical laser. Now, this one's really, really cool. Ultrasonic welding. So, in this particular case, you vibrate to bring the weld parts into close contact and to form a bond. The ultrasonics obviously meaning a high energy process, and it's going to be using small thin parts that are going to be necessary to achieve fusion. This also can be done, I think, with plastics as well. Haven't seen this as an action or as many examples of it as we've seen kind of like electron beam, that sort of thing, but you can check it out anytime. So, friction. Also used in metal and metal and plastics. Weld parts by bringing a stationary secondary part in contact with the rotating weld part. Pressure is applied and heat from the friction causes the weld parts to fuse together. Again, very similar in concept to ultrasonic welding, except we're going to do a little bit more spinning than we are just going to be vibrating. So this has a benefit of joining dissimilar metals in the process. Again, also used in plastics. Brazed welding process is used to fill at metal temperatures greater than 840 but less than the melting point of the base metal. You know, pretty much the same concept of taking filler material, heating it up, but not actually melting the base metal. You're just using the filler to be the bonding component. The filler metal is not distributed by capillary action, which will play into our topic coming up. So in the welding process, you're typically going to see the normal tail with whatever identification you have. For example, SAW or SWEBW, that kind of thing, still shows up in the tail. By the way, while we're here, take a look at this. Any extra process or information on a welding process that goes with it is just shown by a dash extra information. For example, shielded metal arc welding might be draw it here, SMAW, but they may throw a dash MA to stand for manual, or maybe a dash SA for semi-automatic, or whatever the case may be. So the tail and information are always the same, with just dashes to show extra things on top of the initial information. While we're on the topic, though, of some extra processes, let's take a look real quick at brazing and soldering. Alright, now to clarify on brazing, we're going to be talking about the major issue being capillary action, what that looks like. Brazed welding is not the same. Well, I mean, it's essentially the same in some concepts, except the brazed welding doesn't actually work by capillary action. Capillary action is essentially the concept that if I take a piece of toilet paper or a paper towel and I stick it in a tank of water like this at this step, yes, the water soaks the towel right here, but what happens over time, and you probably know this, is that the moisture gets pulled up vertically against gravity in the paper towel. So basically the dryness draws the moisture vertically and overcomes gravity. So the potential capillary action means the potential can overcome forces against it. Force of gravity, for example. So a capillary action is used in a lot of applications. In this particular case, in brazing, the idea is that the actual filler material gets drawn into the part beyond where the actual welding occurs. Brazed welding, however, doesn't go further than where the case may be, or where the actual welding occurs. So slightly different. I think I may have actually worded it wrong, but you got brazed welding, the BAW, and you've got the brazing, which is not the same, which is actually just, I think, B. Okay? So two difference. The key thing is capillary action. Filler materials can honestly be the same in some cases, just slight variations in the process. So break it down a little bit further. Key takeaways there. Brazing, same temperature, greater than 840, but less than the base metal, so you're not melting the base, and does use capillary action. Soldering, used heavily in electronics and plumbing, same process, metal is joined by the filler, by capillary action, temperatures less than 840 and less than the melting point of the base metal. So 840 is our key point here. So if it's brazing, it's over 840. If it's soldering, it's less than 840. Both cases, though, use capillary action, and both cases the melting point of the base metal is not exceeded. So for example, here's a demonstration of brazing using a heavy torch. We've got our filler metal right here. We've got our copper pipe, looks like, and we're heating it up. And notice that the filler material will actually just be drawn into this joint between the two. One of the advantages of this particular process is the reduced heat. Without having so much heat, we won't potentially deform any of our base metals that we have here. Another application to keep in mind, or another component to this, if you're actually in practice, is the use of flux at these joint points to sort of facilitate that capillary action even more. Now, comparatively, and we can always see cool pictures of that, and by the way, for safety's sake, keep in mind that this is one of those things you don't want to be breathing in these fumes any more than you want to be breathing in any others. So keep that in mind in the overall process. Another thing to note too, actually I'll point this out, is the heat is being applied beyond the actual filler material. So they actually get the heat into these zones, which draws that filler material to it, which is that capillary action I was referring to. Soldering, however, you'll notice is done heavily in electronics, And this involves a tip of some type of hot soldering iron to generate the heat, and then your filler material brought in as well. Flux is sometimes added to the process, and the filler material basically joins in. Now in this particular case, here's a nice little graphic. So what they'll do is they'll heat up the filler material into like a little puddle, and they'll let it cool and tie two joints together, that sort of thing. Again, there are fumes associated with this process, so you don't want to breathe those in any more so than anything else. Another point is the fact, yes, this is below the 840 degrees mark because you notice we're not using an open flame to make this happen. Just using a typical soldering iron that you can plug right into the wall. That's not a very big picture. Let's see if we got another one. There's a good example right there. A little bit of solder to create the joint. This is your soldering iron. Still works by capillary action. Whether or not the flux is used may vary on applications. I've seen it used, I've seen it not used, so it kind of depends. Really depends on if you can't get your actual solder to flow or anything else. But I'm no expert on that part. Here's another graphic on brazing versus soldering. Although they do show that they're using a torch on both, which technically you can use a torch on plumbing as well. The filler can actually be done this way too, so you can actually see both these processes. I guess you can call them soldering either way. It depends on your overall temperatures. But you can see your filler material being applied and the technique of how you can do the joints and how they're actually put in. Notice the brazing is sort of like more of a welding application, where soldering is really dealing with just letting the capillary do its thing. Alright, so that's a good stopping point. We'll see you on the next one.